Well, good morning and welcome to Statistics Day 5. So today is kind of a big day. We're going to talk about sampling distributions. And I'm actually going to split up Day 5 into two different lessons. So today you're just going to get the first half of it, and you won't have any homework on this stuff today. So Statistics Day 5. Start with the warm-up. Yesterday we talked a lot about different types of surveys. So let's read through this. Howard collected fish eggs from a pond behind his house so he could determine whether sunlight had an effect on how many of the eggs hatched. After he collected the eggs, he divided them into two tanks. He put both tanks outside near the pond, and he covered one of the tanks with a box to block out all sunlight. State whether Howard's investigation was an example of a controlled experiment, an observation, or a survey. Justify your response. Okay, so we've got three choices. We've got controlled experiment, we've got observation, survey. If you want to think about this for a second, maybe pause the video and think about which would be your answer and why. All right, ready to talk through this? Okay. Now the big thing we talked about yesterday was controlled experiment. Experiment has to impose, not oppose, it has to impose a treatment. The control group, the control part of that means you split into two groups. And that's how most experiments are usually run. One group gets the treatment, and one group gets no treatment. And the hope is that by splitting them into two groups and giving one group a treatment and one group not a treatment, you'll be able to see if that treatment had an effect on the thing you're looking at. We talked a little bit about that yesterday with the placebo. Observation means there's no treatment, and you're just observing some kind of characteristics. And a survey is a type of observational study where you specifically ask questions, but you don't impose a treatment still. So if I read this, you want to know whether sunlight had an effect on how many of the eggs hatched. So sunlight, you would call that the response or the treatment. So already you have to tell me which type it is. You tell me it's a controlled experiment. It's a controlled experiment because there is a treatment. One group gets the sunlight, one group doesn't get the sunlight. And the effect on how many eggs hatched, yesterday we would have called this the response variable. We're looking at if sunlight affects this. So it is a controlled experiment because there's two groups. One gets the sunlight, one doesn't get the sunlight. So we can see if that one piece affects the response variable. Okay, so controlled experiment. Random fact of the day, vultures can fly for 6 hours without flapping their wings. Wouldn't that be nice? You could take a little nap as you soar around the world. Okay, so today we're talking about sampling distributions. Today, the first part of this, we're just going to talk about sampling distributions of sample proportions. Okay, so if we were in person right now, if this wasn't on a video, it'd be a little bit easier to show you this because normally I have a bag. In my bag, I have some different colored chips. And we have to decide, I want to know what percentage of the chips are, let's say, red. Now, I, in my head, know because I've set up this bag, but you have no idea what percentage of the chips or even how many chips are in the bag. What we're going to do to figure that out is I could just dump out all the chips and then count how many are red. But what if there's 1,000 chips in there? That'd be kind of obnoxious to count how many of those 1,000 chips are red. So what I can do is I can take 4 smaller samples and see in those 4 samples what percentage of them are red. We're going to take 4 samples and get 4 sample statistics for proportions. Now when I say proportions, we're going to look at when I pick out these chips, the number of what I want over the total number drawn. So for example, if I am looking at, let's go with red, what proportion are red, I'm going to count how many reds I get out of the total number that I pick out of this bag. Each one is called P with this little thing over it. And this little thing has a very technical term. It's called hat. This is P hat. And P hat is just the proportion of one sample. So let's go back over here. I've tried to make a fake bag. So here's a bag. There's some reds, there's some green, there's some yellow, there's some blue. Some percentage of them are red. Let's say I'm just going to choose 5 random chips. I'm going to try to kind of close my eyes and just quickly go 1, 2, 3, 4, 5. How many red did I get? I got 3 out of 5. So for my first trial, I would say P hat is 3 out of 5. Okay, so that doesn't tell me how many total red chips were in that bag, but in my one trial, 3 out of 5, that's 60%. So maybe 60% of them are red. Let's go back and try again. So again, I'm going to kind of not look and just try to draw 5 out. So 1, 2, 3, 4, 5. How many red did I get that time? None. Okay, well that's weird. So that could happen though. So this time P hat was 0 out of 5. Okay, let's do another trial. Okay, let's go 1, 2, 3, 4, 5. What did I get? Got 2 out of 5 that time. So P hat for trial 3 was 2 out of 5. And then lastly for trial 4, my last trial, let's go 1, 2, 3, 4, 5. So I got 2 out of 5 again. What's that tell me? Well, that gives me some idea of what percentage are red. Do I think 0% are red just because trial 2 I got 0 of them? No, of course not. There's some red in there. Do I think 100% are red? No, because I didn't get all reds every time, so 100% definitely aren't red. So it's somewhere between 0 and 100%. Do you think 75% are red? Or 80%? Probably not 80% either, because 80% would be 4 out of 5, and I didn't get any of them that were that high. Do I think 10% of them are red? Maybe, but this would be pretty high if 10% were red. What's really in the bag? We want to know the population characteristic for all these proportions. One way I could do it is I could take average. So if I take the average of all the P hats, so if I do 3/5 plus 0/5 plus 2/5 plus 2/5, divide them by 4 because there were 4 trials. Let's see what I get. So 3 out of 5 plus 0 out of 5 I don't really have to write because it's not going to give me anything, but we'll put it in for good measure. And 2 out of 5s. So I want to take the average of all my P hats, divide it by 4. What do I get? 0.35. And we call that P instead of P hat. So based off of all of my P hats, if I average them together, I would say maybe about 35% of these chips are red. So we can guess approximately 35% of chips are red. I still know what the actual number is, and I'll tell you that later. But what we just did was we did a small sampling distribution. So each of these was a sample. All of them together is called a sampling distribution. And the average of all of those samples in my sampling distribution approximated the true proportion in the bag, the true population proportion. So let me write that in some confusing statistic words. The mean of sampling distribution of sample proportions, so the mean of the sampling distribution of sample proportions will be approximately equal to the true population proportion. Now, the first time I read this, I'll admit I had no idea what they were trying to say. It's confusing to read. But let's break this down. In statistics, when you hear mean, what do you think of? Average. So this is saying the average of the sampling distribution of sampling proportions. Again, these four values, each individual one is a sample proportion. All of them together is the sampling distribution. So it's the sampling distribution of sample proportions. And the average of all of those will be approximately equal to the true population proportion. So the actual number of chips that were, proportion of chips that were read. Now down here it says, if we draw more for each trial, increase the sample size. So here my sample size was 5, because each sample I took 5 chips out. Let's increase the sample size to 10. Do you think these proportions will become more spread out, or will they be more clumped together? Well, hard to say. Let's try it. So now I'm going to choose 10 chips every time and count how many are read. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How many did I get? One, 2, 3, 4, 5, 6, 7, 8, 9, 10. I got 3 out of 10. So my first p-hat value down here was 3 out of 10. Okay, let's try it again. Okay, here we go. 1, 2, 3, 4, 5. Oops. Let's try this again. We'll reset. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How many I read? 4 out of 10. So this time I got 4 out of 10. And we'll do one more trial. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That was 9. What did we get there? 2 out of 10. Okay, so what am I going to get if I average these? Well, hopefully you can tell. The average is 3 out of 10 plus 4 out of 10 plus 2 out of 10 divided by 3. 3 out of 10 plus 4 out of 10 plus 2 out of 10 divided by 3. 0.3, or 3 out of 10. So the average is 0.3, and that would approximately be equal to the true population proportion. Now up here, we said about 35% of the chips are red. Now, about 30% are red. And in actuality, a quarter of them were red, 25%. So increasing the sample size made the results closer to the actual true value. And that's usually true. If I increase sample size, I'm going to get a better representation of what the true population proportion is. Think about the extreme case. I did 5 and 10 for my sample size, but what if I did 2? If I only took 2 chips out, a lot of times I'd have 100% red, and a lot of times I'd have 0% red. That's not a good representation. But if I take 10 chips out, most of them came out to be about 25%. You're not going to get 10 out of 10 red probably, and you're not going to get 0 out of 10 probably. So conclusion here is, as sample size increases, the sampling variability in the sample proportions decreases. Again, probably kind of confusing, so let's break it down. As sample size increases, so as the number that I pick out in each sample increases, the sampling variability, so the difference in the p-hats, the difference between the p-hats also decreases. So basically they're saying these values should be more clumped together. Think of this, 0.6 to 0, that's a huge variability, it's a huge difference, 60% to 0%. 30% to 40% to 20%, less huge. And if I took 100 chips out, it would be even less huge. And the average of them all should be closer to the true population proportion. So whenever we talk about variability, how spread out something is, you should be thinking of standard deviation. So if the variability is decreasing, you could say, so the standard deviation is also decreasing, becoming less spread out. Okay, now again, why do I do this? What's the purpose of it? Well, in theory, if I had 10,000 chips in a bag and I wanted to know how many of them were red, you sitting there counting 10,000 chips would take a long time. But if you just did some trials, let's say you even did 20 trials of picking 10 chips out, averaging them together, that would still give you a good estimate of the true proportion, and it would take a lot less time. So instead of having chips in a bag, let's say we used our calculator to simulate instead. Because we can save time by simulating this scenario using our graphing calculators. We're going to use the population proportion of 20% for selecting red. We will simulate using the sample size of 20. We're going to draw 20 times. So how we're going to do this is we're going to make a list of random numbers. And I'm going to choose 1 to 100 just because those are easy to divide up. If I want 40% of my numbers from 1 to 100 to be red, numbers 1 through 40 can be red. That means the other numbers, 41 through 100 in this case, are not red, in this case blue. What you choose for your random numbers doesn't really matter as long as 40% of numbers are red, because that's the qualification. That means the other 60% of numbers are not red. Now, just as a side note, I could have also said, let's say, make our random numbers 1 through 10. What numbers would be red? 40% of them. So 1 through 4 are red, and not red would be 5 through 10. So again, you can choose the range of numbers you use as long as 40% of them are red. All right, but let's use 1 to 100. On new calculators, you're going to go to Math, over to Probability, and you want randint. It's going to say lower, which is the lower number you want, 1. I'm going to go to 100 for my upper number, and n is the number of values you want, the number of random numbers. I want 20. If I hit paste, you'll see exactly what you see if you have an old calculator. You'll just do 1, 100, comma, the amount of numbers you want. Now, another thing I want to do, it says we want to store this list into L1. So if I store this into L1, then I can scroll through my numbers and see them easier. So I'm going to go to Store, STO, second one, L1, hit enter. So there, it generated these random numbers, 2, 93, 84, 26. And now if I go to Stat, Edit, 2, 93, 84, 26, we have those same numbers in there. It's just a little bit easier to scroll through and see them all. Okay. So now what we're going to do, we're going to go to that Stat Edit, we're going to count up the numbers that are between 1 and 40. And that's going to be our p-hat value. Now when you do this on a homework or something, let me move this over. Your numbers, if you tried this on your calculator right now, you probably got different numbers than me because they're random. That's the purpose of a random number. So I need you to list out what numbers your calculator actually gave you. And this is a little tedious, sorry, but there's no way for me to know if you're doing it right if I don't have these values. So I've got 2, 93, 84, 26. So 2, 93, 84, 26. Then after that, I've got 73, 25, 11, 74. So 73, 25, 11, 74. 23, 60, 82. And if I scroll down, 94, 50. And what else have I got? 10, 41, 65. And then my last row is going to be 36, 82, 73, 3. 36, 82, 73, and 3. All right, I want to count up how many mean red. That's the numbers 1 through 40. We've got 1, 2, 3, 4, 5, 6, 7, 8. So my first sample proportion, my first p-hat value, 8 out of 20 or 40. And that's pretty darn good because 8 out of 20 is 40%. It's exact. Now, it might not always be that way. Let's do another p-hat value. So I'm going to do math, probability, pick random numbers between 1 and 100 again. And I'm going to store this in L1. And now when I go to stat edit, I have a whole different list of numbers. All right, so let's list them out again. We've got 39, 37, 24, 19, 24, 79, 46, 34. 72, 95, 73, 14. 38, 57, 59, 34. 'And the last one is 23, 20, 8, 90, and 20. Okay, count up how many are red. So the numbers between 1 and 40. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, that time a lot of them were. That's 60%. Now we know 60% of the numbers between 1 and 100 are not 40. But one sample could have something that extreme. Okay, so I think you get the idea. I'm not going to keep writing these all out, but I do want to get 2 more samples. So let's do this 2 more times. So stat, oops, what am I doing? I need to go probability. So math, probability, random int. I'm going to do 1 to 100, and we want 20 random numbers. We're going to store that in L1. And I'm just going to go to stat edit. Instead of listing them all out, again, I'll need you to list them all out on a homework or something, but let's just count. We've got 1, 2, 3, 4, 5, 6, 7, 7 of them this time. So my p-hat for this time was 7 out of 20. And let's just do it one more time. So stat, oops, math probability. Keep messing that up. I want 20 random numbers again. We're going to store that in L1. Count how many are between 1 and 40 when you go to stat edit. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 of them this time. Okay, so there's my sampling distribution of sample proportions. What do I get if I take the average of all those? Now we know the true population proportion is 40% here. So I would hope that when I average these all together, I get close to 40%. Looks like I'm going to be a little bit higher. Hit enter, divide by 4.475. So they're saying the true population proportion here is about 0.475, which is close to 40%. It's not exactly, but it's a good estimate of it. Okay, so this is another way to simulate picking chips out of a bag without actually picking chips out. Okay, a couple more examples. Simulate 10 flips of a fair coin. Record your steps and observations. What is your sample proportion of tails? Okay, what do we know the true proportion of tails should be if I'm flipping a coin? It's a fair coin, which it says it is 50%. Okay, so the big idea is we need 50% of random numbers to mean tails. So, what numbers do you want to pick? Well, if I use the numbers 1 through 10, what numbers would tails be? 1 through 5. What numbers would heads be? 6 through 10. 50% of the numbers are tails, 50% are heads. Or, what if I just pick the numbers 1 through 2? What would tails be? 1. What would heads be? 2. As long as 50% of your numbers mean tails, you can do that. So you can do 1 through 100, 1 through 10, 1 through 2, whatever. As long as 50% are tails, 50% are heads. I'm just going to do 1 through 10 because that's what I started with. I'm going to go to math, probability. You want 1 through 10 this time. And how many coin flips was I doing? 10. So I need 10 random numbers. And we're going to store those in L1 so I can go back and look at them. So stat edit. And again, I do need you to list them out so that I know what you're getting. So we have 56228. 56524. And what's my p-hat value? I'm looking for 1 through 5 to mean tails. So 1, 2, 3, 4, 5, 6, 7. It's kind of an extreme case. P-hat was 7 out of 10. So one sample, you could get 7 out of 10 heads or tails. That's not crazy. If you did that 20 times, I might start questioning if your coin was fair or not. But one sample, you could get 7 out of 10. Okay? Let's do one final example. 10% of all Skittles are green. 90% are not green. Stimulate randomly selecting 20 Skittles. Record your steps and observations. What's your sample proportion of green Skittles? P-hat. Well, we know that the probability of green has to be 10%. So let's choose the numbers 1 through 10 because it's easy to make 10% of those green. What would green be? Just one number, like 1. So not green would be 2 through 10. 10% of the numbers are green. The others are not green. 90% of the numbers are not green. I'm going to go to math probability 1 through 10. We want, how many are we selecting? 20 of them. So back to 20. Oops, I wasn't on the home screen. Got to get back to the home screen every time. Sorry about that. Through 10 with 20, and I'm going to store that in L1. If you're doing this on the homework, list it out for me so that I can see it. We've got 9, 2, 1, 10, 2. 9, 2, 1, 10, 2. 1, 6, 1, 9, 10. Then we've got 8, 10, 7, 2, 10. And then finally, 6, 7, 8, 8, 10. I was looking for my proportion that were green. So those are all the numbers ones. So 1, 2, 3. So my p hat, a little more than 10%. It's 3 out of 10. But that's my sample proportion of green Skittles. Just kidding. I didn't take 10. Sorry. 3 out of 20. And 3 out of 20 is closer to 10%. 0.15. So that's close to 10% being green. I could believe that. All right. So that's not the end of the notes, but that's where we're going to stop today. So if you wanted to do some of the homework, if you have this, you won't be able to do the front of this homework yet at all. The back you could do. The back is asking you to do some of these random sampling distributions and asking some questions about it. So you can do the back of the homework if you want to get a head start. If not, just use tonight to get caught up on any old statistics homeworks you haven't finished yet. And we'll finish off this video on Monday. See you then.